So welcome everybody for the last lecture of this conference, and this will also be Professor Blekherman's last lecture in his mini course. So we are really looking forward to this last lecture, which will contain a lot of important results and also applications of what he has been discussing so far. So looking forward to this lecture. Yeah, Greg, please. Yes, over to you. Yeah, thank you.
Thanks. Yeah. Thank you for coming. Yeah, I know it's late, and also this is the last lecture in a long week. Okay, so let me recall what we did last time. So last time, let me kind of formally state the thing that we proved at least one direction of. So let's suppose that we start with a totally real irreducible variety. Then non-negative polynomials, non-negative quadratics on x are always sums of squares if and only if x is a variety of minimal degree. Okay, and let me recall for you what is the variety of minimal degree. A variety of minimal degree is a variety that satisfies this inequality with equality that we proved last time. So degree of x is equal to codimension of x plus 1, but for any variety, this inequality is always true. And varieties of minimal degree are varieties for which this inequality is actually equality. And so the thing that I want to emphasize about the proof, so we proved one direction. We proved that if x is not a variety of minimal degree, then non-negative polynomials are always bigger than sums of squares. And the thing that I want to emphasize is that, you know, how did the proof go? The proof really it started with convex geometry. That's the thing that I want to emphasize, because I think it's kind of it's a nice blend of ideas. So we start with convex geometry. We say, okay, if non-negative polynomials are equal to sums of squares, this is also going to be true for all of the faces of the cones. So let's look on the boundary. And when we look at the face, you know, basically faces of the cone of non-negative polynomials are given by polynomials that vanish at a single point. And then we realize that actually when we look at the cone of non-negative polynomials and sums of squares, what we're really doing is we're taking the variety and we're projecting away from a point. And then, you know, then we can kind of take this equality on the faces and continue going until we project away enough, and we end up with a hypersurface. And then for the hypersurface, understanding the case of equality between non-negative polynomials and sums of squares is easy. And then we end up with, you know, one half of the theorem, or one of the directions of the theorem. Yeah. And so what I really like here is the blend of, you know, the combination between convex geometry and algebraic geometry sort of coming together. Okay. But now you might ask, so what are varieties of minimal degree? And for example, how do they fit into Hilbert's theorem, right? So now we have more cases of equality, probably. What are varieties of minimal degree? So actually these varieties have been studied classically. So they were classified by Del Pezzo and Bertini. So Del Pezzo did the case of surfaces, and Bertini extended it for n-dimensional varieties. So what are varieties of minimal degree?
Irreducible ones or all?
Well, no. So here, that's right. So actually, there is no notion of minimal degree for reducible ones. So this only works for irreducible varieties. Okay. Yeah. So yeah, and there is also some disagreement in mathematics literature. So when some people say variety, they really mean irreducible, right? But when some people say variety, that means that it may or may not be reducible. May be reducible or not, right? But yes. But yes, here when we say variety of minimal degree, this only corresponds to irreducible ones, because there is no good. Yeah, we will talk about this a little bit later. There is no good notion of minimal degree for reducible varieties. Okay. So X is a variety of minimal degree. only in the following. So case one, so what are varieties of minimal degree? So one, the case of hypersurfaces is easy. Degree of x is equal to codimension of x plus 1. So the only way that if x is a variety of minimal degree for a hypersurface is if a degree is 2. In other words, it's a quadratic hypersurface. So one, we have quadratic hypersurface. Two, there is very interesting. So remember in Hilbert's theorem, there is this exceptional case of ternary quartex, which corresponds for us to the second Veronese of P2. This is an exceptional case also in this theorem. There's one exceptional case, the second Veronese of P2, which corresponds to ternary quartex for non-negative polynomials and sums of squares. And three, this is the most interesting class, the largest class, is a rational normal scroll. So this includes, for example, all of the cases of univariate polynomials. These are the Veronese embeddings of rational normal curves. And also includes the quadratics, because that's just the projective space. Okay, so let me maybe say a few things. So what about quadratic hyper? So now let's think about equality between non-negative polynomials and sums of squares. What other things do we learn besides Hilbert's theorem? So quadratic hypersurface, this case was known before for non-negative polynomials and sums of squares. This is what is in engineering is usually referred to as S-lemma. It's a very useful statement, but it really deals with just basically with something defined by one quadratic equation. So it says that, if you have a quadratic that is non-negative on a hypersurface defined by one quadratic equation, then you can write it as a sum of squares modulo the equation of the quadratic. So the second Veronese of P2, that of course we saw that was already part of Hilbert's theorem. This is really ternary quartex.
What is the name that you wrote there after the quadratic hypersurface?
S-lemma. I don't know what S stands for, but it is just called S-lemma.
Sorry, so S-lemma says that it's a variety of minimal degree, or that Px equals sigma x?
That Px is equal sigma x.
Okay.
I mean, the fact that it's a variety of minimal degree is very easy by definition. So the fact that Px is equal to sigma x in this case is referred to as the S-lemma.
Yeah.
Okay.
Okay, so now rational normal scrolls. So the case of equality between non-negative polynomials and sums of squares also for scrolls was known before. So let me explain, but what are rational normal scrolls? So one way of understanding it that these are rational normal scrolls. These are, well, in some one way of saying that these are some special toric varieties. But let me just let me give you sort of let me explain what's happening here kind of in a very quick way. So toric varieties are given by monomial embedding. So what I need to do is I need to specify a collection of monomials. So let's say, so I give you, so usually what people do is they draw a picture with lattice points. And what do these lattice points correspond to? These lattice points, so let's say that this is 0, 0. Okay, so then these lattice points correspond to monomials, right? So here, because it's in the plane, they're going to, so these correspond to exponents of monomials. So when I draw a picture like this, what I really think about is a map that sends xy into a pair xy into xy raised to this power. So for example, 0, 0 means that I raise x to the 0, y to the 0. This will become 1, right? Then I have a point 1, 0. So that is going to send me to x. Then I have a point 2, 0, that will be x squared. Then I have a point 0, 1, that will be y. And then I have a point 1, 1, this will be xy. Right, and now what do? I have to projectivize this map. So I take all of the segments, all of the lines through these points, and that will give me my toric variety. Okay, so again, toric varieties are given by monomial maps, and you record monomial maps by drawing a collection of lattice points. And the lattice points denote the monomial. So this is how I read this picture. It corresponds to this map. Does this make sense? Are there questions?
Questions? Okay, no question. Online audience? Okay, yeah, looks like no questions.
Okay. Right, so yeah, so rational normal scrolls correspond to special. So what usually also happens is that if you want to consider nicer toric varieties, you will take all of the lattice points inside the polytope, not just a random collection of lattice points, but all the lattice points inside the polytope. And so rational normal scrolls correspond to sort of very special polytopes. So what are polytopes for rational normal scrolls? So what you do is you take the standard 0, 1 simplex. So you take 0, 1 simplex in Rn. And then what you can do is, so that will be, the simplex corresponds to just the embedding of the projective space. So that's not very interesting. You add one more dimension in n plus first coordinate. We take some heights. We have a freedom of selecting some non-negative heights. We take heights, so I don't know, h0 up to hn. And what we do, so we have this n-dimensional simplex, and now in the n plus first dimension, we just say how far we go up, right? These are these non-negative heights. And this gives me a polytope, and that's those are polytopes of rational normal scrolls. So let's do an example. So an example that I can draw. So I'm going to take n is equal to 1. So I'm going to take the 0, 1 simplex, right? So I'm going to draw it like this. And now in one more dimension, in the x direction, I'm going to select heights, and I get to select 2 heights. So I get to take all of the lattice points inside this polytope. So I go, I don't know, height 3 or 4, however you count here, and maybe this height here.
Okay. Sorry, once again, what is the 0, 1 simplex in Rn?
So 0, 1, I'm sorry?
For n equals 2, how does a 0, 1 simplex look like? Maybe?
Yeah. So for 0, so what would we do in 2 dimensions? So we will take 0, 1. So this will be like this.
Okay.
Right. And now we're going to raise it in the 3rd dimension. Right. We're going to raise it up. Right. So the heights will tell me how far up I'm going to go.
Right.
It's going to be sort of slightly harder for me to draw, but we're going to go heights and we're going to go up.
Okay. Thanks. And then you take the convex solution, right?
Right, and then we just take all of the lattice points inside this polytope, but all of the lattice points will be just exactly, the 0, 1 points, and and how up, but yeah,
right.
Take all of these. And these guys lead to more interesting occurrences of equality between non-negative polynomials and sums of squares. But now, one of the things that we want to do is now we want to understand the reducible case. So reducible case is also interesting because, for example, we saw from the matrix completion problem, we naturally are left, there we naturally deal with reducible varieties because they're just unions of coordinate spaces. So now what about reducible case? So as I mentioned before, there is really no good notion of minimal degree in reducible case. Why? So if your variety was equidimensional, meaning that all of the irreducible components have the same dimension, then you can still define minimal degree in the same way as we did. Then everything still kind of works. But the problem is, what about if you have components of different dimension? Because remember, how did we define degree? We said the degree is equal to sort of the number of points that I see as I step a variety with a space of a correct dimension. But the problem is that if I have the components of different dimension, I need to step one of the components with a linear space of one dimension, and I need to step the other component with a linear space of another dimension. So it doesn't make sense. I cannot really see all of the components by doing things, with a linear space of one dimension. And that also explains why it is, the notion is still okay in the equidimensional case. So it's not really clear. What to do. But as I mentioned before, I think it's not hard to show that that the irreducible, if you have equality between non-negative polynomials and sums of squares, every irreducible component must have equality as well. So they must be varieties of minimal degree. So really what we're saying is that we have a collection of varieties of minimal degree, and we need to glue them in a special way. I don't know. And the question is, how do you glue them? How do you glue them in a special way? So we can kind of take inspiration from the chordal case, right? From the case of chordal graphs, there we already have an answer, because so for chordal graphs, the irreducible components are just projective spaces, but because of the chordal structure, this click-sum structure, the way that we glue them together is actually quite special. So let me define this.
So what you're saying is, if you just take any ordinary variety whose components are all of minimal degree irreducible, then that may or may not satisfy Px equals sigma x. But if you have to do them in a special way, then, and what is that special way?
Exactly, that is exactly right. So you cannot just take, you cannot just put together some some varieties of minimal degree together in an arbitrary way and then say, okay,
right,
non-negative polynomials will be equal to sums of squares. The way that you put them together is actually very special.
Okay, thanks.
Okay, so let me define, so if I have two varieties, now here they may be reducible or not reducible, or irreducible, doesn't matter, x and y. We say that they are linearly joined if I look at x intersect y, and I look at what at the linear span, right? How much do they span? This is equal to the linear span of x intersect linear span of y. Right, so one inclusion is trivial, right? This inclusion is trivial. The other inclusion is it's what makes it special. Okay, and what's going to be good for us is so now we have varieties of minimal degree, and we want to get the union by linearly joining things, but the order in which we do things may matter. So let me try to So the idea is, so now X, so let's say X1 union union Xn is good, but I'm going to replace good with a more mathematical term now, but I'm not going to, I'm only going to introduce it a little bit later. X1 union Xn is good if there is an ordering but in order to not introduce indices, let's just pretend that 1 up to that n is this right ordering, such that X2 is linearly joined to X1. X3 is linearly joined to X1 union X2. X4 is linearly joined to X1 union X2 union X3, and so on, up to Xn. So Xn is linearly joined to X1 union X2 union Xn.
Sorry again, and where are these varieties sitting?
So they're all inside some projective space. I guess I used N, so let me say inside PK. So these are projective varieties, but now they are there. So the point is that somehow I'm gluing them together, and in a nice way. The nice way this nice way may depend on an ordering. So what I mean is that if I take them if I start gluing them in different order, they may not look to be linearly joined.
Right.
But
right.
all I need for there to be is there exists a right ordering, some right ordering in which way, so that when I glue them together, every gluing is linear joining.
Right. So this is like the clique tree decomposition of a chordal graph.
That's exactly right.
Yeah.
That is exactly right.
And sorry, and what was span again?
Span, just the linear span, right? So inside project, if you want to think of them not sitting inside
so
the
you
project,
unprojectivize
inside Rn plus 1.
Right. You unprojectivize, take the span, and then project.
Right. I mean, you can also talk about linear span in the projector space, but it's most familiar to just put them inside linear space and say.
Okay. Yeah. Sure. And you said you will replace the word good with something more mathematical.
Yes, exactly. So there is a term for these guys. So, but first before I get into the terminology, I wanted to just explain the content of this. That's exactly right. So this is exactly like like how do you glue cliques together inside the chordal graph, right? You cannot necessarily glue them in arbitrary order, but in a good order, things happen exactly like that.
Can you explain how the X2 is linearly joined to X1? Is it we are taking subspace of dimension 1 or?
Wait, I'm sorry. Say your question again.
Yeah, how the linearly joined is defined? Are we taking a subspace of dimension 1 or something?
So okay. So these guys, I mean, it's kind of hard for me to draw a picture, but let me try to draw something that maybe is kind of a not linearly joined, right? So let's say I have a curve in 3 space, right? And this curve spans the entire 3 space, right? And now I have another curve, and there is another curve in 3 space, and and if I take the linear span, the curve spans the entirety of the 3 space, so they do not lie in the plane, right? So now what do I want? I want the span. So x intersect y is just 1 point. Yes. Right. So what I want is that the span of x intersect y is actually the span of x intersect span of y. That's not that's not going to happen here, because the span of x intersect y is just this pointer. If you want to linear, I mean, this is going to be a line, but the span of span x intersect span y is going to be all of R3, something like this. Does that make sense? So by span, I just mean linear span. So, so these guys, they do not necessarily span the whole space. So for example, what would be something that is linearly joined? Let me try to give you, so I mean, for example, if I take something like 2 lines in the plane, right? I mean, because for when I take the span of a line, it's just still going to be, so here, if you want replace if I don't draw projective picture, then instead of span, take affine span. right? So here is the span. These two guys are linearly joined. Why is that? Because, you know, so this is X, this is Y. So the affine span of X is just the still line X. The affine span of Y is still Y. And then when I take, you know, X intersect Y is this point, the affine span of this point is the point. But it is true that the point is span X intersects span Y.
Yes, yes, got it. Yeah, got it. Thank you.
Yes, looks good. Yeah, looks good.
Actually, wait, hold on. Maybe this is not, I feel like I stated something incorrect. So the linear joint is stronger than that. Sorry, I realized. It's not that the span of X intersect Y, it's just X intersect Y. So you really need to join them along linear spaces. Sorry, that was my fault. Yeah, so you really, you glue them along linear spaces. So X intersect Y is span X intersect span Y. So these are varieties glued along linear spaces. Okay, and right. So what does good mean? So good actually has a mathematical term, and these are called varieties. These are called two regular varieties. But what does that mean? So what does two regular refer to? Two regular refers to what is called Castelnuovo Mumford regularity.
And I think that was exactly the condition in your chordal graph thing in your online archive notes, right?
Yes, that's exactly right. Yeah. So this is, yes, this referred to Castelnuovo Mumford regularity. That's exactly right. And so what is this? So I kind of wanted to explain what it is. I mean, one way of saying what is Castelnuovo Mumford regularity 2 is exactly this, but that's not how it is defined. It is a theorem due to, I think, Eisenbach, Green, Hulick, and Popescu, that these are what two regular varieties look like, right? But so I kind of, in some sense, I did things backwards, right? But what are two regular varieties?
Sorry, just before that, can I just quickly go to the definition upstairs for the
yes.
good, for the two regularity?
Yeah.
So yeah, just the first line just says that take a variety which is x1 union x2 union xn in pk, where the xi's are irreducible, and this is two regular if there is an ordering. That's the theorem.
Exactly. If there is an ordering and you glue them along subspaces, and not only that, but it still needs to be special, so that X intersect Y is span X intersect span Y.
Right. Okay.
Yeah.
Yeah. Thank you.
Okay. So now I'm going to just very briefly explain what is happening here. So one way of studying, you know, I mean, in a sense, what is the point of algebraic geometry? It's studying geometric properties through equations, right? And now, I mean, that's one way of understanding it. And so now the question is, so what can you say about some properties of equations, right? So let's say that we have, let's just sort of forget about geometrical content, and let's just think about like ideals and generators. So that's more like commutative algebra. Right. So so the question is, if I give you, for example, let's say two quadratics, and I want to understand what are relations between them, right? Well, one possibility is that these two quadratic, you could say, well, maybe there is a linear relation, right? Meaning that, you know, maybe there are constants C1 Q1 plus C2 Q2, so that this is equal to 0. But that is, you know, that is really not very interesting. Because essentially this just means that these two quadratics are multiples of each other, right? The equations are multiple of each other. So, I mean, that in some sense, you know, if you think about the variety that they defined, it just means that you had the same quadratic. So then you could ask, okay, but then maybe there could be something a little bit more interesting if instead of taking coefficients that are constants, I'm allowing myself coefficients that are polynomials. Okay, so now I want to write down a relation, you know, something times Q1 plus something times Q2 is equal to 0, where the coefficients are no longer constants, they are polynomials. And such a relation is called a syzygy of Q1 and Q2. And so well, there is really an obvious syzygy, right? If I take Q1 and I multiply it by Q2 times Q1, and then I take Q2 and I multiply it by minus Q1, right? That will always be equal to 0. Right? So there is this sort of obvious syzygy. Right, where I take coefficients Q2 and minus Q1. But sometimes, and if I take two quadratics that are random, there is really not going to be any more interesting syzygies than this. These syzygies are only going to be obvious syzygies. Right? The only interesting syzygies are obvious syzygies. But now but if I take special quadratics, then interesting things might happen. So for example, if I take xy and xz, then these two guys have a linear syzygy, right? Because I can take this, I can multiply it by z, and I can take this guy and I can multiply it by minus y, and I can subtract, and this will be equal to 0. Okay, so sometimes, if I take special polynomials, that they might have kind of more interesting syzygies. And so what does 2 regular mean? So, right, so I look at x, but now instead of looking at x, I look at the ideal of x. So these are all of the equations, these are all of the polynomials that vanish on x, all of the equations defining x. This is a finitely generated ideal with, let's say, this generators q1 up to qk. So first of all, in order to be 2 regular, all of the q's need to be quadratic. So the vanishing ideal of x needs to be generated by quadratics. But moreover, all of the syzygies between all of these generators are linear. So, or in some sense, all of the syzygies are generated by linear syzygies, because I can get more syzygies. Even here, I produce for you 1 linear syzygies, right? But here I can multiply everything by x, for example, right? And I can produce. You could say, okay, well, this is not really. It's not really more interesting syzygies. It was really generated by multiplying by z here and multiplying by minus y there. So all of the syzygies are linear syzygies, or if you want to be more precise, they're generated by linear syzygies. But actually, that's still not enough. You can take this process further, because now you can analyze syzygies between syzygies. So then you look at syzygies, and now all syzygies between syzygies are also linear. And now actually you keep going, and this process is guaranteed to terminate. As you analyze syzygies between syzygies between syzygies between syzygies, this process is guaranteed to terminate by a theorem of Hilbert. And what we're really constructing is what is called a free resolution of ideal of x. But the point is that in order for variety to be 2 regular, as you analyze syzygies between syzygies between syzygies between syzygies, they all remain linear until you run out of syzygies, and that's when you obtain the full free resolution. So yeah, I do not want to dwell on this too much. As I mentioned, by a theorem of Eisenbach, Green, Hulick, and Popescu, these are really varieties of minimal degree that are glued together in this linearly joined way.
So isn't this is also the NP property, right? What is called the NP property?
Let's see. So, well, it's not quite. So really, it would say, yeah, so this is property NP, but maybe for P is equal, this is kind of where you can take P to be as large as possible. If you want, you take P to be codimension X, or maybe you can even think of it as P is infinity. I mean, the process is going to terminate. But yes, that's right. So, and property NP is that your resolution stays linear for P steps. But here your resolution
Yes.
stays linear for as many steps as it needs to take.
Ah, so it's you're asking for a linear resolution.
Exactly. That's exactly right.
Okay.
That's what two regular means. It means that the resolution is linear. It's not that it's linear for a few steps, it's linear for all of the steps.
Oh, okay. So varieties with linear resolution are exactly those that are glued, that have this gluing. Is that the
That's
statement?
exactly right. Yes.
Okay. Yes. Questions?
Or I guess you have to be a little bit careful because these are these are guys that are generated by quadratics and they have linear resolution. You
Quadratics.
have more.
Sure.
You have more examples if you don't insist on quadratic generators, but the resolution will still be linear. So you insist on linear syzygies, but you don't insist on having certain degree of generators.
Yes. It's quadratic. Okay. Any questions from the online audience? Okay. Yes. Looks like we can go forward. Yeah.
Okay. Yeah. So that's sort of the main theorem that basically, that non-negative polynomials are equal to sums of squares if and only if x is too regular. So maybe let me write this down. That's the final generalization. So yeah, so the proof of this is more complicated, but still one of the things that I wanted to emphasize that in the proof of this, you still use this projection away from points that we used for proving, one direction for irreducible varieties. So, okay, so I think maybe at this point I still have a little bit of time. So I just wanted to explain maybe why are sums of squares interesting, not just from like theoretical point of view, but also from a more practical point of view. But so this we will kind of switch gears. So are there any questions about this part before we do that?
So here, do you need x to be quadratically generated or not? Here.
So in order to be, so two regular includes quadratically generated.
No, the left-hand side.
For pure, if your ideal is not generated by quadratics, it will be problematic. So you don't need to assume it.
Okay, right. You wouldn't even define
the equality between the codes of non-negative polynomials and sum of squares is going to give you that the ideal is going to be generated by quadratics.
Oh, okay. And so we didn't see the proof of this this characterization for irreducible varieties, right? Completely. I mean, we saw part of it last time. Is that correct?
That's correct. I didn't really give you the proof of the other part.
Okay. Any?
Let me think about this. What can I say about? I mean, there are several. Okay, I mean, let's see. Then I will run out of time to do things for application. But let me maybe let me try to give you some idea about the proof. And the proof, well, there is one way of doing a proof that is really modeled on Hilbert's way of doing the proof for ternary quartics. So let me maybe explain to you Hilbert's proof for ternary quartics. And then, and really this proof can generalize to any variety of minimal degree. Using some, you don't really need the full classification, but you need some properties of variety of minimal degree in order for the proof to go through. But let me tell you how Hilbert's proof works, and then I can give you a pointer to where to look for the generalization. But it's really exactly the same.
Yes. Yes.
Modulo some, modulo some properties that you need to see that they generalize. Okay. So what Hilbert actually proved for ternary quartics is that not only are all ternary quartics sums of squares, but they're actually sums of 3 squares. Okay, and not only, and this proof was interesting because I think he used some ideas that were kind of ahead of its time before kind of formal development of topology really happened. But anyway, so let me tell you how to do this. So, right, so here we're looking at P34 and sigma 34, so ternary quartics, and I'm taking 3. So what I want to show is that every non-negative polynomial is a sum of 3 squares. So I'm going to look at a map. Let me define a map, maybe phi, from R6 cross R6 cross R6. Or really what I want to do is maybe from P5 cross P5. Well, okay, let's do R6 cross R6 cross R6. No, yeah, this is great. Yeah, R6 cross R6 cross R6 into ternary quartics. So these are 6s, these are really quadratic. So maybe I should have written it like this. This is Rx32. These are 3-dimensional. So I take 3 copies, Rx cross 32, Rx cross 32, Rx cross 32. Right, and I map it into ternary quartics. And what do I do? So I take Q1, Q2, Q3, 3 quadratics, and I map this triple Q1, Q2, Q3 into Q1 squared plus Q2 squared plus Q3 squared. Right, and what so in the end, I end up, this is going to be a sum of 3 squares, and I want to show that this map is onto P34. All right, so what I want to show is that image of phi is all of P34. Okay, so now I'm going to be a little bit imprecise in how I do things, but all of these things can be sort of straightened out. But let's so the idea is, okay, let's imagine that that my image is not P34, right? Then there must be a point. That is kind of on the boundary of the image, right? And that is what I mean. I'm being slightly imprecise. So if image of phi is not equal to P34, then there should be points on the boundary of the image. So now, where do points on the boundary of the image come from? Well, they come from points where if you look at the Jacobian of the map, the Jacobian of the map is not full rank. Right, so the Jacobian, now I'm just thinking about this from the point of view of differential geometry, right? I have this map, and let's try to analyze the Jacobian of the map. And really, it is enough for me to understand what happened to the map that sends Q to Q squared, right? Because then basically when I'm adding, I'm just taking sort of 3 independent copies. Right, so what is going to be the Jacobian of the map that takes Q to Q squared, the differential or Jacobian? Or what you want, if you want, what is going to be sort of the span, right? What I want to know, I don't really need to write. What I want to know is what is the span, or what is the tangent space. So if you want really, what I have here is I have a map that sends Q to Q squared. So what I have inside here is the variety of squares. And what I want to know is what is the tangent space to this. And the tangent space is equal to the ideal generated by Q. So in degree 4. So what does this mean? what this means is that, my Q is a quadratic, and I take a map from Q to Q squared. And the differential, the row span or the column span is the ideal generated by Q in degree 4. So these are all multiples of Q. So now when I have a map, then I take the triple, like, Q1, Q2, Q3. Sorry, like this, Q1, Q2, Q3, and I send it to Q1 squared plus Q2 squared plus Q3 squared. Then the differential here is going to be just the ideal generated by Q1, Q2, Q3 in degree 4. And so, okay, so now what is happening here? Now let's try to count dimensions, right? Let's try to count how much do Q1, Q2, and Q3 generate in degree 4? Well, how much does Q1 generate in degree 4? Well, I can take a quadratic and I can multiply it by any quadratic, right? And there are 6 dimensions of quadratics. So the ideal of Q generated by Q1 in degree 4 generates something 6-dimensional, right? The ideal generated by Q2 is also 6-dimensional. The ideal generated by Q3 is also 6-dimensional. So you would think that what I get is something that is 18-dimensional. Right, but that is actually really way too much, because the whole space of ternary cortex is 15-dimensional. So I'm definitely overcounting. What am I overcounting? I'm overcounting overlaps between the ideal generated by Q1 and the ideal generated by Q2, for example. And these overlaps exactly correspond to syzygies, right? Because, the ideal generated by Q1 includes Q1, Q2, but the ideal generated by Q2 includes Q2, Q1. So I definitely overcounted this one, right? And so you can see that by this logic, I overcounted at least 3 things. Are there questions?
Yes. Any questions? The difference is turning out to be 1.
Hi, so you said like there are 16 in number, so we counted extra 1, right? As in, sorry,
No,
there
there
are
are
15
18 in number. 6 times 3. 6 times 3 is 18, so we overcounted by 3.
Oh, all
at
right,
least.
all right.
Right, and so now I'm telling you which 3 we overcounted by. So Q1, Q2, there is an overlap like this. And of course, the same is true for Q1 and Q3 and Q2 and Q3. So we overcounted at least 3 things, right? And 18 minus 3 is 15. And so in fact, what is true is that if Q1, Q2, Q3 are what is called the regular sequence, in other words, have no common complex zeros, then our dimension count is correct. Then the dimension of the ideal generated by Q1, Q2, Q3 is 15. So basically what it says that if Q1 and Q2 and Q3 have no common complex zeros, now let's see if this condition makes sense. Because we have 3 variables, but these are 3 homogeneous variables, right? We're really inside P2. We really have 2 parameters and we have 3 equations. So because we have 3 equations and 2 parameters, we expect them to not have any common solutions, right? So it is expected almost all of the time, Q1, Q2, and Q3 will have no common solutions. And so then the dimension will be 15 in degree 4. And so this means that basically your map is going to be locally surjective, right? Because the Jacobian is going to be full rank. So this means that you're going to map little ball around Q1, Q2, Q3 around this point, around this triple into an open ball around Q1 squared plus Q2 squared plus Q3 squared. So these guys cannot possibly be on the boundary of the image, because the image actually contains an open ball. And so for such Q1, Q2, Q3, Q1 squared plus Q2 squared plus Q3 squared is in the interior. Okay. So now what happens if they have a common complex zero? Well, these are real equations. If you have a common complex zero, this zero comes in complex pairs. So if Q1, Q2, Q3 have a complex zero, then they actually have a conjugate zero. Then they have a pair. Then there is a pair of zeros. There is a pair of common zeros. And this means that the dimension of the ideal generate, because the idea is that, you know, what can Q1, Q2, and Q3 generate? If they all vanish at 2 points, then whatever they generate will also vanish at these 2 points. So which means that they cannot generate something that is more than 13 dimensional. They have to generate something that is of codimension at least 2. Right? Because of this pair of complex zeros. Right? Because they all lie inside they all lie inside linear subspace of ternary cortex that vanish at these 2 points. And then, you know, if you vanish at this 1 point, that will drop the dimension down by 1. If you require vanishing at a second point, it's going to drop the dimension down by 2. Okay, and so what does this mean? Because again, now this differential Jacobian has corank at least 2. So these points can also cannot be boundary points. So since corank of Jacobian is at least 2, these also cannot be boundary points of the image. Because on the boundary, you need to be a corank 1. The boundary should be a hypersurface. So then, what is the only possible case of boundary points? So the only other case Q1, Q2, Q3 have a common real zero. But then if we look at Q1 squared plus Q2 squared plus Q3 squared, these guys, because Q1, Q2, and Q3 are 0 at some point, Q1 squared plus Q2 squared plus Q3 squared, that will also be 0 at some point, is also 0 at this point. And this means that Q1 squared plus Q2 squared plus Q3 squared, this guy lies in the boundary of the cone of non-negative polynomials. Because as we discussed, what is the boundary? These are things with real zeros. And so now let's recap what happened here. So we looked at this map phi that just takes 3 quadratics and then maps them to their sum of squares. Right? And now we found that actually the only boundary points of the image are the boundary points of the cone. Right? There are no boundary points on the interior, and this means that this map is actually onto. Now, as I said, I was being a bit imprecise, but in like using the term boundary, but anyway, but all of this can be straightened out. But intuitively, this is really what's happening. And this is really Hilbert's original proof. And so you can use exactly the same proof to prove the equality for any variety of minimal degree. Let me tell you where one can look for this.
Yes. So the last part. So why did we get a contradiction there? So this cannot possibly be in the boundary.
No, so, right. So what we found out is that the only boundary points of the image are actually boundary points of my original cone, right? If basically what I said, and I said what I claimed, that this is not totally precise, but if the cones were not equal, there ought to be boundary points on the interior, right? Boundary points that do not belong to the boundary of the whole cone. But now we found out that there are no boundary points on the interior, and this means that the two cones are equal.
Okay. Yes. Yes.
Right. So, and the paper where this is generalized to varieties of minimal degree is called low rank sums of squares on varieties of minimal degree.
Mhm.
Okay, so I think, yeah, that basically means I'm essentially out of time. So I think I'm not going to try to say any more, but I'm happy to answer any questions that you have.
Yeah, thank you so much, Greg. Let's thank Greg for the very, very interesting series of lectures. And yeah, patience in answering many of our questions, very basic questions sometimes. So more questions? So, there is a more refined version of this this connection between regularity and the sums of squares being equal to the positivity, right? Is that correct? In one of your papers, you have a more refined version of this. So, for instance, if you're, or at least maybe maybe thinking in terms of the NP property. So, so given NP property, does that translate into something about sums of squares? This is positive. Yeah.
Right. All right. Yes, that's right. So you can that's true. So what one can do is so once you know, I mean, you can also ask, what happens if the cones are not equal? Right.
Yeah.
What happens? So let's say, so for equality, this is as good as it gets. That's basically the complete characterization. But you could also still ask, let's say that the cones are not equal. But maybe you could say that, let's say your variety is close to a variety of minimal degree, right? Can you say it's close to being equal? Or, what can you say about, are there still some properties that transfer? And the answer is yes. There is at least a little bit. That's right. And that has to deal with property NP. So this is the number of steps for which the resolution stays linear. Okay, I will try to very briefly explain what's happening, because the way that I chose to do things in these lectures did not really touch on this topic. But let me say what's happening here. But in a sense, it might not make too much sense. I'm sorry, but otherwise it will just take too long. Okay.
Yeah.
So you look at the cone. You can look at the dual cones, Px star, and then sigma x star. Okay, and so for Px star, this dual cone we discussed, the extreme rays are just point evaluations. Now, what about sigma x star? So sigma x star, these are, what are these? These are linear functionals, such that, so let's see, these are linear functionals on quadratics, such that they are non-negative on squares. Because non-negative on sums of squares is the same as being non-negative on squares. But now, instead of thinking about it like this, you can associate to this guy a quadratic form, QL, which is just L of Q squared, but this QL is now a quadratic form on the linear guys, because what do? You know, I take a linear guy and I square and I apply the linear function that gives me a quadratic form.
Mhm.
And now, so basically the way to think about the dual cone to the sum of squares is that I have a bunch of quadratic forms. All right, so what I really have is and as I said, this will not necessarily make much sense because I'm doing things very fast. But what I really have, sigma x star, is really an intersection of a cone of big. And now, you know, if I'm in the sigma x star, then this quadratic form needs to be a positive semi-definite because it's not negative on squares. So sigma x star is really an intersection of a cone of positive semi-definite matrices with some linear subspace. And I can analyze extreme rays of this intersection. And one way of saying that the px is equal to sigma x, and that can give you a different way of proving equality and non-equality, right? So these guys are equal, sort of, if and only if the dual cones are equal.
Yeah.
And this means that, you know, all extreme rays of sigma x star, extreme rays of sigma x star, are point evaluations. And point evaluations correspond to rank 1 quadratic forms. So basically, another way of thinking about this is the following. I have an intersection of the cone of positive semi-definite quadratic forms with a linear space. And what I want to see is that all of the extreme rays of the intersection are of rank 1. But usually this is very special. If I take a convex set, like an iPad, like a square, and I intersect it with a linear space, you know, what I often will get is I will get extreme points. The intersection will be a segment, and the extreme points of the intersection are not extreme points of the original set. But here I want the extreme points of intersection to be rank 1 matrices, which are actually extreme rays of the original cone. And so the property NP. So now, if these cones are not equal, there exists extreme rays of extreme rays of sigma x star that are not of rank 1. And you can ask, what about, you know, what ranks are possible? And the rank of the smallest rank of an extreme ray that is not rank 1, we call the Hankel index Hankel index of x. And indeed, you can prove that there are at least some inequalities between Hankel index and this property NP. That's what I wanted to say. So property NP has some bearing on what are possible extreme rays of the cone dual to the cone of sums of squares. And so if you have extreme rays that are of rank more than 1, so the cones are not equal, if you have property NP from any P, this prevents you from having extreme rays of low rank.
Yes.
That's what's happening.
So in the cases, in the classical case, just with the Varieties varieties, so is the NP property of our Varieties embeddings, has that been determined for all Varieties?
Unfortunately, no. It is no. So NP is known for the plane for P2, and is also known, I think, for third Veronese embeddings and for fourth Veronese embeddings. But after that, it is not known.
Right.
It would be very nice to determine what it is.
Right. And
yeah.
And
I think
that might
it's referred to as a Ottaviani-Paoletti conjecture.
Okay. Okay. And has this, and that will have some implications on giving more information. That will give more information probably on these classical cases, right?
That's right.
Sums of squares.
That's correct.
Seems very interesting. Yes. Okay. Any other questions from the audience? The online audience? Any questions? Apurva?
No, Greg answered everything that I had. Thanks again, Greg.
Any other questions from the online audience? Okay. All right. Let's thank Greg again for these series of lectures.
Thank you for coming, everyone. I know it's been
Insights.
long time and it's quite late, so thank you.
Thank you. Thank you. Thank you so much, Greg. Yes. Take care. Hope, yeah. Hope we can meet in person. We all can meet in person sometime. So,
You too.
thank you.
Take care.